previous presentation, I clarified the combinations with repetitions, permutations, all these kind of things. So that's the basic combinatorics. So counting how many times something happens. And you see, in all the cases, we got explicit formulae which consisted only of finite number of additions and multiplications and division too, but all the divisions were seen as producing finally some natural number again. So all these functions I've been talking about are simply functions from natural numbers into natural numbers, right? And now let's jump through all the other types with this I was discussing in the first presentation for this week. And the most difficult way how to understand a function was a function which is well defined, but no one can compute it, right? So I was having a sort of quite bad example there, unpleasant example, but there are many simple ones, right? So imagine you have a coin and you throw the coin and count how many times you get one of the two sides, right? Or you throw a dice with six possible results, as we know all from childhood or still are playing these games. So you have got these 6 possible results, and the function we consider could be that we shall be, so we are going to throw the dice many times, and after throwing it n times, we want to know how many times we got a 1 or how many times we got a 6. Or any other combination. So you can just come up with dozens of different easily built functions this way, but all of them are very well defined, because once we go through this throwing, so after throwing 100 times we shall know all the previous 100 values. But first, we never can know it up to infinity, because we can't throw it infinite times. And second, we don't know anything now before starting the experiment. So it's a well-defined function, and what we can do is to count what we call probability. The probability with which we can expect some of the results. And that's already at the core of data science, right? So let's have a look, and I will just try to present it as a very simple example of building a mathematical model, a mathematical theory, absorbing or adding enough abstraction to have the simplest possible example you can have in your mind working as a general tool, right? And here the first thing is that, for example, with the dice, we of course should expect that the dice is not optimal. So the first guess that it should be 1/6 probability to get each of the results with each throw as not realistic. So if we just cut it ourselves by our knife from some piece of wood and draw the values on the sides, then perhaps we shall end up with something rather like this. We shall have individual probabilities of the individual sides of the dice, but there will not be 1/6. The only request we have to pose is that the sum will be 1. And that's not strange, right? That's easy. And then the easiest way how to create such a model is that you will have, say, a space of all the individual possible values. So that's the elementary events. That's the elementary events. And then each subset of this could be considered as a possible result. So if we say there should be an odd number, that would mean that we are considering the subset of 2, 4, and 6, right? And so on. And then if we think that the things are very much classical, the simplest way, then you can imagine that each of the elementary events appears with the same probability, and mutually disjoint events will simply come with probability, which is a sum of those things. It's similar like in the elementary combinatorics. I didn't say the main rule. So if you count the things and the individual steps are independent, you multiply the numbers, and if you divide the possible result in some mutually disjoint possibilities, then the number of occurrences are added together, right? So it's the rule of addition and multiplication in the elementary combinatorics. And the same will be here in the probability. So the classical probability says that if I've got the whole space of all the possible events, for simplicity we consider only finite ones, omega, and I get a subset of size, well, this way written A, so that's the size of A, then the probability is just the relation. So the frequency of appearance is the same for each elementary event, and therefore we expect that this should be the right toy model for probability, and it is, right? And then we can make it into a mathematical theory by providing the definitions. So this is what we call probability functions. So that's a function describing probability, and we know that if we are not interested in what will happen, we consider all the omega, then the probability must be 1, because it's absolutely sure that it happens. And if we take empty set, then it must be 0, right? And that's achieved by this already as a consequence. So that's typical for mathematical theories. You don't want to come up with all the conditions, only those which are independent, and then the rest is following as a consequence. And that's exactly here. If I wish that whenever the subsets are disjoint, then the probabilities are added. And then of course each subset has got the complementary subset, and the complement to whole of omega is empty set, and so the empty set must have probability 0, right? And we request that probability of everything is something between 0 and 1 this way, right? So that's it, right? So this is the probability. There are some simple consequences of our definitions, right? So one of them was this one: AC is the complement of A. And also what's clear is, if we want to add the probabilities properly for two sets, then of course what we are doing is we can sum the probabilities of each of them, and then we have to take into account that those who are in the middle have been counted twice, so we have to subtract them. And now the sort of, not miracle, but the beauty of mathematics or mathematical reasoning comes, because of course at the level of the classical probability, where everything is just divided by the common factor, the omega, the size of the whole space, this is obvious, right? Because this is just counting the points as I pointed to the picture. But because we introduce the probability by the set of axioms, and we are deducing all the other properties, this will be a consequence, right? And so this holds true. So our intuition says it must be like that by counting the points in the sets, but the result is that this holds true for all the probabilities, right? Wherever you define a probability the right way, it's happening this way. So there are more discussion of that in the set, in the text, but let's have a look at the generalization of this, because of course what happens if we start thinking about more subsets, right? More events. So let's have 3 events, A, B, and C. So if we count them together, then we of course counted the points which are in 2 of those twice. But if we subtract them properly, so this is the sum of all, then we subtract all the intersections. But there is a problem, because those who were in all 3 of them were actually subtracted too many times, and then we have to correct this, and this is just adding the probability of the complete intersection. Right, and this is what in combinatorics is called inclusion-exclusion principle. And again, by counting the points in the sets, you can verify this directly. It's not such a big deal. But what we are doing in the text is proving a theorem which actually goes much further. It goes much further because here you see you have the arbitrary models of probability. So there is a sample space, a finite set. You fix some set of events, so it's not necessarily all the subsets, and you pick up k subsets in the set of events, so those who have got a probability. And then here the formula simply generalizes in a straightforward way what we saw by our toy model expectation in the case of k equals 3. And now the nice thing is that it's easy to prove. Actually it's an induction procedure, so we know it's true for k equals 1, it's obvious, it's an empty claim. For k equals 2 we have proved it already. So let's assume we know it for all k from 1 to some k, and some fixed k, and the goal is to prove it for k plus 1. And then by this argument it holds true for all the natural numbers, and that's what the theorem says. And so usually in mathematics, if you have such a theorem which is based on the induction principle, so the main difficulty is to guess the result, and then the induction step is not that difficult to do, right? And that's exactly this case. Right, so that's a very remarkable step, I think. So if you think about it in detail, and I advise you would, so something which in combinatorics is very generally used and clear, just counting the number of possibilities. Therefore it's called the inclusion-exclusion principle, because you exclude all the overlaps, and by excluding too much you have to add those back, and then you add too much, so we have to subtract again something. That's what's happening. But this is true for all the probabilities of this simplified kind with finite sample spaces. Right, and now I'm coming to a more interesting thing, right? So it's interesting, I haven't used this at all yet. So let's draw at least something here. So I'm just talking and chatting instead of explaining something by writing, but never mind. So what are independent events, right? So of course, in the classical probability, you can say that independent means that the subsets are mutually disjoint, but essentially we should like to see it more clearly and more seriously, in such a way that we are interested in stochastic independence, which means that we are questioning whether the probability of the A and B occurring at the same time, so the probability of the intersection, is the product of probabilities, right? So this is a more general wish. And you can just read through these examples that it's not that easy, right? So you have to take this with some care. But what's nice is that if we define events to be stochastically independent, if the product rule holds for all the subsets of our set of events, right? So that's important, that we want to have the stochastic independence for all the subsets. So each couple of them is mutually independent, and then the same for each triple, etc. Right? So that's the thing. And now a nice observation is that just if we have two stochastically independent events, then the probability of A intersection with the complement of B is again the product. So this means that if we have a set of stochastically independent events, then we can replace any of them, any number of them, by their complements, and it will be again stochastically independent. That's quite important. So this is what I had to say about the toy model of probability, and in a second I will continue in another presentation with what we call conditional probability, and that starts to be already interesting.